Okay, so in this video, what I'll do is a bucket rope walk related problem, and yeah, let's get started. So I start with this particular problem. A bucket that weighs 4 pounds and a rope of negligible weight are used to draw water from a well that is 80 feet deep. The bucket is filled with 40 pounds of water and is pulled up at a rate of 2 feet per second. But water leaks out of a hole in the bucket at a rate of 0.2 pounds per second. Find the work done in pulling the bucket to the top of the well. So as is common in this kind of problem, the first thing that helps to be done is to draw a diagram to visualize what has been described. So let's assume this is the bucket. It has a handle with a rope attached to it, and the rope is hanging up somewhere, and where maybe someone is pulling it or whatever is pulling it. So the bucket itself is 4 pounds. The bucket is 4 pounds. And the bucket is filled with water. The bucket is filled with water. Maybe let me shade this. It's filled with water. Filled with water. And this water weighs 40 pounds. Okay. And it's pulled at a rate of 2 feet. So this whole setup is 80 feet deep. So we want this to be pulled from a well of 80 feet deep. Okay. So water leaks at a rate of 0.2 pounds per second, and we also told that the bucket is pulled at a rate of 2 feet per second. So what we can do is, suppose this stuff moves a tiny x distance, a tiny x feet distance. So we can say, suppose so assume I think the best way to start is say, okay, at x feet distance, or at x feet height, above the bottom of the well. Okay, what will happen? So we are told that the bucket is pulled up at a rate of 2 feet per second. So which means that as the distance from the bottom of the well increases up to the top of the well, the time that the bucket is being pulled also increases, right? So what this means is that the rate of change of this little distance or height with respect to time is given as what? 2 feet per second. Okay, and from here we can instantly get that what? X is equal to 2t plus a constant. Think of this as you differentiated a function and you get 2. So what is that function that you differentiated with respect to time and you get t? It's exactly something that looks like this. Okay, But how can we find this constant C? How can we find the constant C? Now, we are told that at time is equals 0. We are not told, but we can think of it that at time equals 0, this bucket is at the bottom of the well. And what does that mean? If we are taking x to mean height above the bottom, then at time equals 0, we have now moved the bucket any distance. So x is equal to 0, right? So we now have 0 equals what? 2 into 0 plus what? C. And from this we get that C is equal to 0. So indeed, we have the relationship that x depends on time by 2t. Okay, so actually from here we can get that t is equal to what? X over 2. We can call this equation 1. Alright, now we are told that the weight, water leaks out of the bucket at a rate of 0.2 pounds per second. What does that mean? As the bucket rises up above the bottom of the well, the amount of water in the bucket actually decreases, right? So we can say that the weight of water in the bucket decreases with respect to time. So what we can do is say, let W be equal to weight of water, right? Then by that single information, we have that what? Rate of change of W with respect to time is given as what? It is decreasing pounds per second. Remember, a decreasing function has a negative derivative, right? Because as the height, as time increases, which means the bucket is going up, the amount of water in the bucket decreases. So that's how we get this relationship. So from here, think of what function did you differentiate to get this. It will be something like W is equal to negative 0.2 t plus a constant d, right? Okay, but at time equals 0, what is the weight of the water? Let's think about it. At time equals 0, the bucket is at the bottom of the well, which means it has not moved any distance. Okay, so what that means is that at time equals 0, weight is exactly the full amount of water in the bucket, 40 pounds. So this gives us that what? 40 pound equals negative 0.2 times 0 plus d, and from here we get that d is equal to 40. So clearly we see that the relationship between weight and time is what? 40 minus 0.2 t. And now it helps to return back to this equation we already have. So we want to characterize the force as a function of distance. So plug in t from there, we get this is actually 2 over 10, and then t is x over 2, right? Okay, so this is now 40 minus these two cancel, we have x over 10. Awesome. So this is the weight of the bucket, weight of water at x height above at the bottom of the well. Alright? Now recall that total force required to carry load x feet high. So F is now what? Dependent on x, and this is nothing but weight of, so this is weight of bucket, which is like empty bucket, plus weight of water that is carried in the bucket, and plus okay, so we are meant to add the weight of rope, but notice that what? We were told that the rope has a negligible weight, right? The rope has a negligible weight. So notice that rope has a negligible weight, which means weight of the rope is sort of zero. You can approximate it by 0. So indeed, the force required to pull this up is equivalent to the weight of the bucket plus weight of water. Now we've gotten the weight of water, and we're told that the weight of bucket is 4 pounds. 4 pounds. So this force is actually 4 plus weight of bucket, weight of water, which is 40 minus x over 10, and everything equals 44 minus x over 10. Okay, recall that but work done, so we now want to find the total work done in raising the bucket up, is equal to what? Integral of force with respect to distance. But the well is 80 feet deep, so we are going to integrate from 0 to 80, and we're given the force to be this, so I just plug in. This is integral from 0 to 80, 44 minus x over 10 dx. Alright, so if you integrate this, we get 44x minus x squared. 2 times this, we get 20, and then we evaluate this from 0 to 80. So plug in 80, the upper bound, minus 80 squared divided by 20. So I think I've computed this just not to waste time. This one is 3520 minus this one is 320, and this is nothing but what? 3200 joules. Okay, so this is the total work that is required to be done raising this load, the bucket plus the water that is leaking at a particular rate, to a height of 80 feet. Alright? Okay, so let me do another problem that looks like this. I think this problem is in the practice. There's 2 practice, so let me get the problem. Alright, so I'll paste. Okay, So the problem says a 5-pound bucket containing 10 pounds of water is hanging at the end of a 300 feet rope which weighs 15 pounds. The other end of the rope is attached to a pulley. The rope is wound onto the pulley at a rate of 3 feet per second, causing the bucket to be lifted. Find the work done in lifting the bucket 200 feet if the water leaks out of the bucket at a rate of 1/4 pounds per second. So as before, it helps to draw something to visualize what we're doing. So this is kind of the setting. So here we are told we have a pulley. This is actually attached to a pulley. So the bucket is 5 pounds, right? The rope is 300 feet. Rope is 300 feet. 300 feet. Okay. And this rope also weighs 15 pounds. Right? Okay, so this gives us that our weight per feet is going to be what? 15 pound divided by 300. So this will be pound per feet. So let's keep that in mind. Alright. So find the work done in lifting the bucket 200 feet. So we want to lift this bucket. 200 feet. Okay. So like in the previous problem, what we'll do is to take a little height at x feet above the level of the load, which is when no work has been done. So we're told that whether at x feet or at any point in time, the rate of this movement is what? With respect to time is 3 feet per second, right? So think about it like the previous problem. As we raise the bucket or the load up, time increases, right? Which means that this thing has a positive slope or derivative. So from here we get x is equal to 3t plus a constant. So think of what did you differentiate to get 3. It's actually something that looks like this. And again, since we are considering x to be height, which means it starts from 0, so at time equals 0, the height is nothing but 0. And this implies that 0 is equal to 3 times 0 plus c, which gives that c is 0. So x, which is height above the level of the load, depends on t by this equation. And from here we can get that what? T is indeed x over 3. Maybe call it equation 1. Okay? Now, let's use the other information that that the water leaks out of the bucket at a rate of 1/4 pound per second. So what does that mean? That if let W be weight of water at x feet, high. Then as we are told that as the load rises up, the amount of water in the bucket decreases since the water is leaking, right? Which means as time increases, the load or the water content decreases. So given that the rate is 1/4, that simply means that change in water with respect to time is going to be -1/4. And think of the function you differentiated to get this. It's going to be something like this: -1/4 t plus a constant d. Now let's interpret what this means. When time is 0, it means the whole load is, nothing has happened to the load, which means the amount of water in the bucket is 10 pounds. No water has leaked, right? So that means that at time equals 0, weight of water is 10 pounds. So plug this into this, we get 10 equals -1/4 times 0 plus d, and this guarantees that d is equal to 10. So weight of water in particular depends on time using this relationship, 1/4 t. Awesome. But notice that time depends on the height above the ground with this relationship. So from equation 1, we have this is 10 minus 1/4 into x over 3, and this is from 1, right? So this gives us 10 minus x over 12. Interesting. So at x feet high above the usual level of the load, the weight of water in the bucket is given as this. This is nice. Now the next thing is to find the work done in carrying the bucket, the bucket, the rope, and the water high through what? X feet. Now recall what we have here, that the amount of pound of the rope per feet is 15/30, right? So if you carry the bucket or the rope, if you raise the rope x feet high, then you have 300 feet minus x feet rope being raised up at x feet high, and that's exactly the load you are carrying on the rope. So at x feet high, 300 minus x feet times 15 over 300 pounds of rope is pulled up. So at x feet high, this is the amount of rope that is lifted up. All right. So total force required to pull the load, which is the water, the bucket, and the rope, x feet high, is what? F. As before, it depends on what? Weight of bucket which is empty bucket, plus weight of water, and plus this time around the weight of rope is not negligible, so we have to add the weight of rope. And we've computed this except for the weight of bucket, which is given. So weight of bucket is 5 pounds, plus weight of water is 10 minus x over 12, plus weight of rope, which is given as 300 minus x times 15 over 300. Interesting. So let's simplify this. Let's simplify this. So this plus this is 15 minus x over 12. Open up this times this is 15 minus this divided, I think 15 into 300. So we see 300 divided by 15 is 20. So this is x over 20. So add this and this, we get 30 minus we have the LCM of this and this is 60, I think. So I'll have 60. Then 12 into 60. 60 divided by 12 is 5. So I have 5x. Then plus what? Plus 20 into 60 is 3. So I have 3x. And that's it. So this will be 30 minus, this is 8x over 60, which is 30 minus 4 is common here, so I have 2. 4 divided this is 15. Awesome. So this is the force that is needed to keep that load at x feet high, right? Now we need to calculate the total work that will be done in raising this thing bit by bit, bit by bit, bit by bit, up until 200 feet high. So we conclude work done will be nothing but integral from 0 to 200 f of x dx. And f of x dx is, we've seen, 30 minus 2x over 15 dx. So whatever is left is to integrate. So I have 30x integral of this minus this will have squared divided by 2. So we'll cancel this 2. So I have x squared by 15. Then we evaluate from 0 to 200. Okay. So plug in, I have 30 times 200. 30 times 200 minus 200 squared divided by 15. So I have calculator here. 30 times 200 is 6,000 minus 200 squared is, I think that should be 40,000 divided by 15. Okay, so the LCM of this and this is 15, so I'll have 15. This will be 15 times 6,000. 15 times 6,000. 6,000 times 15. This is 90,000 minus, oh, this is 40,000, sorry. So 40,000 90,000 minus 40,000 is 50,000. Divide by 15, which is indeed, I think 5 is common, so 5 into 50,000 is 10,000. 5 into this is 3, so 10,000 divided by 3 is roughly 3,333.33 joules. So this is the amount of work that is required to raise this load, as the setup is 200 feet high. Okay, so I'm thinking it's good to solve one more problem, in particular from the book. So let me see. So I go to 6.4, exercise 6.4, and in particular, let me look at, I think problem 17 would be nice. So problem 17 looks related to this. So I'll go back and I paste this. So this one says a leaky 10 kg bucket is lifted from the ground to a height of 12 meters at a constant speed with a rope that weighs 0.8 kilogram per meters. Initially, the bucket contains 36 kg of water, but the water leaks at a constant rate and finishes draining just as the bucket reaches the 12-meter level. How much work is done? Okay, so as before, it helps to visualize. So something like this. Okay, so the setup is a height of 12 meters, so the total height here is 12 meters. A liquid 10 kg bucket is the height of this at constant rate. So the bucket itself is 10 kg, and the amount of water, maybe I'll shade, amount of water in the bucket is 36 kg. So I have 36 kg of water. Okay, but the water leaks at a constant rate and finishes draining just as the bucket reaches the 12-meter level. Okay, so since we are not given specific rate, we use the same idea as before to derive what this thing looks like. Okay, so let's say at x feet high, so let's say at x feet high, assuming this is 0 level, at x feet high, okay, so do we have bucket lifted from ground to a height of meter constant speed, a rope that weighs, so the rope weighs, this rope weighs 0.8 kg per meter. So at x feet high, the amount of rope that is lifted is the total rope minus x feet, right? So at x feet high, 12 minus x meters of rope is lifted. So this implies that 12 minus x times 8 kg of rope is lifted. It's lifted. So this is mass of rope, right? Lifted. Okay. Again, let's compute the mass of water lifted. So since the water is leaking and it leaks at a constant rate, we can assume that this change in mass would depend on the height above the ground, which is what we have. So just like we did in the previous problems, so we would have 12 minus x, part of it remaining, and then each kg of water out of the 12 would weigh what? We have 36 kg in total height. So each feet above would weigh what? 36 divided by 12. So at x feet high, the amount of water that is remaining is 36 over 12 times 12 minus x, and this would be in kg. Right, so this follows from similar thing we did in the previous problem. We had the specific rate, and that was helpful in deriving this kind of relationship, but we are using the idea of that relationship to solve this problem. Okay, so let's see. Now what is left is the bucket itself is 10 kg. So this is mass of water at x feet high, and this one is mass of rope. This is mass of rope, right? And bucket is what? 10 kg, mass of bucket. And this mass does not change with respect to height, so it's constant. At each point in the lift, the mass of bucket is constant. It doesn't change with respect to x. So total force required to lift the load x feet high will depend on x, and it will be what? As before, this is weight of bucket, empty bucket, plus weight of water in the bucket, weight of water, and since the rope is not negligible, so plus weight of rope that is lifted. So weight of bucket is 10 kg, or weight of bucket is 10 kg, sorry, mass of bucket is 10 kg, plus mass of water is 36 divided by 12 into this kg, and mass of rope is 12 minus x times 0.8. Yes, so these are all masses. Now to get weight, we need to multiply by gravity, since we are lifting up, times 9.8. Awesome. So let me see if I can simplify this out. So if you work this out, 10 times this is 98, plus 12 can divide 36 and you get 4. Yes, 12, 36, oh, 3, sorry. You get 3 times 9.8 is 29.4 into 12 minus x. Then 0.8, let's see, 0.8 times 12 times 9.8 is 94.08. Then 0.8 times 9.8 is 7.84x. So let's work this out nicely. So this is 98 plus 29.4 times 12 is 352.8. Then this is 29.4x plus 94.08 minus 7.84x. Okay, so this is let's add up. So I have 98 plus 352.8 plus 94.08 is 544.88. This one is negative this, which is like 29.4 plus 7.84 is 37.24x. Interesting. So this is the total weight or force that is required to pull the weight x feet high. Now, as before, once you have this, work done is integral over your force. And how many feet high do we want to move? Move the bucket reaches 12 meter level to constant rate and finishes draining just as the bucket reaches the 12 meter level. How much work is done? So we want to push this up until what? 12 meters high. Awesome. Okay, so we plug in. This is integral from 0 to 12, 544.88 minus 37.24 x dx, and I will leave you to finish up this. You should be able to work this out nicely, even though the numbers are ugly, but I think you get the idea. So I'll stop here. Thank you.